In this video, we're going to focus on another application of linear programming, which is transportation planning. There are a lot of different types of transportation planning problem, but the one that we're going to focus on today is um, this scenario where we have multiple sellers and multiple customers at different locations. All these sellers and all these customers are located at different locations, and therefore the distance between each one of them is different. The transportation cost is different. All right. So there is a certain amount of product stored by each one of these sellers at their warehouses, for example, warehouse number 1, warehouse number 2, warehouse number 3. And then each customer on the other side, each customer has a specific amount of demand for that product. Now think of this customer 1. Let's say customer 1 needs 100 units of product. These 100 units, for example, the one demand of customer 1, let's say, is 100 units. These 100 units can come from seller 1, can come from seller 2, or seller 3. So we have 3 transportation paths or 3 routes in order to satisfy the demand of customer 1. Same thing for customer 2, same thing for customer 3 and 4. So let's say I'm just going to do for 4, there's going to be so the demand by customer 4 can be satisfied with the product stored in location 1, location 2, location 3. And indeed, we have 4 customers, 3 sellers. So in total, we will have 3 by 4, 12 routes. Total routes. And the question here is that how much item to sell through each one of these routes, how much item to be shipped from each seller to each customer. And what we want to have is that we want the customers to be happy. We want their demand to be satisfied. And at the same time, we cannot violate, we cannot send more than what is actually stored in a location. So if, let's say, there are 200 units here, you cannot send, that's impossible, right? So you can't plan to send more than 200 units from this location if there's not more than 200 units, right? So you want to satisfy the demand, and at the same time, you have to stay within the capacity of each store, all right? So the decision here is, in this specific example that we're solving, is the amount of products to be shipped from each seller to each customer. The seller, can be also called origin. This can be called destination, because the items are actually shipped from origins, from the sellers, from the distribution center, from the storage, right, warehouses, to the customers, to buyers, to destination. All right. The decision that we want to make, we're going to call it Xij, the amount of product, amount or quantity of product to be shipped from seller I to customer J. From origin I to destination J. This is the decision that we have to make. And we want to make our decisions in a way that we first satisfy the demand. Second, We don't violate the capacity of our sellers. We don't over ship from the each one of these storage places. And our objective at the end of the day is to come up with the minimum transportation cost. We want to find the best transportation schedule. All right, so that is our objective. Now let me get to a very specific example, and we're going to solve it in Excel as well. So our objective in the example that we just talked about is to minimize the cost of shipping goods from the origins to destinations, from the sellers to the buyers, to the customers. So the specific example that we're going to talk about, it's Foster generators problem. It involves the transportation of a product from 3 plants to 4 distribution centers. So it's similar to what we have, 3 plants to 4 distribution centers. All right. So now customer in this case is distribution center, seller is the plant. We're selling from the origin to 3 origins to 4 destinations. And then our decision is how much of production, how much of the products to be shipped from each plant to each DC, distribution center. We have the capacity, 3 months capacity of each plant, as well as the 3 months demand forecast for each one of our destinations, right? And interestingly, the total demand and supply match here. But usually the capacity of our suppliers should be typically greater than the overall demand. If we want to make sure to satisfy the demand, we should have enough capacity provided by our suppliers, right? So, but in this case, they're actually matched. Total supply, total demand, all right? And the graph looks like this. We have similar to what we just had, 3 origins, 3 plants to 4 destinations. And then we have 3 by 4, 12 different routes, 12 distribution routes. And then we also have the transportation cost per unit through each one of these routes. So for example, the cost per unit from Cleveland to Boston is $3. So if you send, let's say 100 units from Cleveland to Boston, it's going to cost you 3 by 100, $300. And so on. So we have all these numbers for all of these routes. Now, like I said, we're going to define the decision variable to be Xij, the number of units shipped from origin I to destination J. Since we have 3 I's and 4 J's, so and therefore 12 distribution routes, we will have 12 decision variables, the amount to be shipped from each destination, from each origin to each destination. And then our objective is to find the minimum total transportation cost. So that is our objective. So, and this is actually the cost table. If we write down the supply and demand constraint, for the supply constraint, the total amount shipped from each supplier, right? So anything that is coming out of origin 1, Cleveland, should be less than or equal to the total capacity of Cleveland. The total capacity, I just want to go back to my graph here. For Cleveland, the total capacity is 5,000. And the items that are coming out of this, that are shipped from Cleveland, can go to Boston. So it would be called X11, X12, X13, X14. The sum of these 3, X11, X12, X13, and X14, should not be greater than 5,000. So that is exactly what we have. The overall shipment from Cleveland Center, Cleveland plant should not go beyond the capacity of Cleveland. Same thing for Bedford and York. So we can just write down same constraint. Just notice the index for the same index for origin 2 for that applies to Bedford plant, and 3 for York. 3.1, 3.2, 3.3, 3.4, less than or equal to the total capacity of York, York plant. Like I said, in this case, we want to make sure that the demand by each customer, by each distribution center in this case, is satisfied. The total items sent to distribution center number 1, which can go, let me come here again, to Boston, the items that are coming to Boston, so it's called X11, X21, X31. The items can come from any of our plants. So X11, X21, X31. The sum of these three should be equal to 6,000. All right? Should be equal to 6,000. And then same thing for Chicago, St. Louis, and Lexington. So you have to have the total items sent equal to the demand. This will make sure that the demand is satisfied. And if we just put everything together and write down the objective function, this is going to be the mathematical formulation of the product. We want to minimize the total cost, transportation cost. So we have 12 routes and we have per unit cost of each route. So if we just take the sum product, that would be our objective. And we have the supply and demand constraint. So this is really the mathematical formulation. I'm gonna now jump on my Excel file and go ahead and try to solve it in Excel. All right, so here I have my Excel file, and here I have all the parameters that we were talking about. The total capacity at each plant. We have the total demand. I mean, all numbers are quarterly in 3 months basis. So for distribution centers, we have the demand, and we also have the cost. So these are cost numbers. So what I'm gonna do, I'm gonna just write down these parameters, and then we go ahead and create the decision variables and objective function, and we solve the model. So let me just write down the cost per unit, and then we have Cleveland, Bedford, York, Boston, seven, 2, and 4, 6, 3, and 5. We have, so these are the costs, and then we have the total supply or total capacity, 5,000, 6,000, 2,500. And then we have total demand of each distribution center. We have 6,000, we have 4,000, we have 2,000 and 1,500. And sum of both total supply and demand is the same. So I'm just gonna move a little down. So decision variables, we said we need one decision variable per each pair of origin and destination. So 12 decision variables. So I'm gonna copy these and paste it here. So let me, and then cost per unit, I'll change it to items to be shipped. All right, from each origin to each one of these centers. And then I'll highlight that. So 12, 3 by 4 decision variables. And then our objective function would be the total cost. All right. So each unit sent from Cleveland to Boston is going to cost us $3. And we're sending, this is actually X11. So 3 by this cell is going to give us the total cost of shipments from Cleveland to Boston. And plus 6 by X21 plus 2 times X31. But I'm just going to use some product function, and it's going to be per unit cost and the decision variables. So this is my objective function, which is actually total or transportation cost. And then for the constraints, we need the left-hand side and the right-hand side. I'm gonna take this, I'm gonna move this from here to a little bit to the right, because I'm gonna write down my constraints here and here. So for each supply center, the total shipped from each supplier is going to be the sum of these numbers. So sum of anything that is shipped from Cleveland. Let me just write down one constraint, and we can always copy the formula. So the total that is shipped from each supplier should be less than or equal to the total available by each supplier. And the total available by Cleveland is 5,000 total supply. All right. Maybe I move my objective function again a little bit to the top here. And I can, so I just wrote my constraints for Cleveland, the supply constraints. I can just drag it down, and it's going to give me the constraints for Bedford and York. Let's see. The sum of items sold or shipped from York should be less than or equal to the total capacity of York. So that will take care of the supply constraints. And we also need to make sure that the demand is satisfied. So total shipped to this should be for Boston, the total amount or the total quantity shipped to Boston is equal to the sum of items shipped to Boston. And I'm going to put the formula that right here. So we want to have this either you can put equal or greater than or equal. Um, doesn't really make any difference because it's not gonna really, since we are actually doing a minimization problem, it's gonna stick to equality even if you put greater than or equal. But I'm gonna go with equal just to uh, actually follow the books mathematical formulation. So we go with equal. So the total shipped to Boston should be equal to its demand, and the demand for Boston is 6,000. So that's my demand constraints for Boston. And if we just drag it to the right, it's gonna make sure to adjust it for other cities. So let's say for Lexington, we have the total amount shipped to Lexington to be exactly equal to 1,500, which is uh, the total demand by this city, by this distribution center. Now that we have everything set up, we have decision variables, we have objective function, and we have 7 constraints. And for each constraint, we have the left-hand side, the right-hand side, and we determine the sign. All right. So all of these 7 constraints are already set up in our spreadsheet model. Now we're going to set up the solver and solve the problem. So if we go to data tab and call the solver, we just want to minimize, make sure to change it to minimization. We want to minimize the objective function. So for me, it's going to be H17. And then by changing my decision variables, 12 of them, and my constraints are going to be supply constraints, all of the left-hand sides less than or equal to all of the right-hand sides. And Excel is going to take the corresponding cells and form 3 constraints here. Add, and then the demand constraints, left-hand side equal right-hand sides. And again, since I took 4 cells here and 4 cells here, Excel is going to identify those corresponding left-hand sides and right-hand sides, and it's going to form the constraints here. So 7 constraints, 12 decision variables, and the objective function, and we want to minimize the cost. Change the solving method to simplex LP and solve it. Okay, I'm not really worried about the sensitivity right now. We can just take a look at the answers, and then answers, I just rely on my results in this table. So as you can see here, my suppliers, so these are the left-hand sides are more important in this case because our right-hand sides are parameters. They're already set, they're already fixed numbers, but the left-hand sides are to be determined by our decisions. So the total shipped from each supplier, as you can see, they're all binding, and our demands are also binding. We are satisfying all demands. We are using up the overall capacity of each plant. And this is how we are using our capacity, our supply capacity in order to satisfy the demand. All right. For example, for St. Louis, all of the 2,000 of its demand is coming from Bedford. And then, for example, New York is only sending to Boston. It had a capacity of 2,500. Everything is sold, everything is shipped to Boston. And then the minimum cost, transportation cost for us in order to make sure to satisfy the demand is 39,500.